that light's always blinking red as well. Wait, it's going to blink red again. Testing.
I replaced this battery just today.
All right, it works out. Thank you. In case this happens again, this is the second time this has happened. Is there a wire that I can unplug and plug back in to fix it?
As long as you don't tell the union.
Okay.
This is the power thing. Pull it out, count to 10, plug it back in.
Got it. Thank you.
Okay, don't tell the union.
I won't.
Okay.
I guess we're recording. I'll delete this part of the video. Okay, so for those of you joining online, you've got sound now. Okay, so zero-sum game. We've got a maximization player. We call him Max. He's got a bounded closed action space, A max. Subset of, let's say, R to the M. We've got a minimization player. We call her min. She's also got a bounded closed action space. Let's call that A min. U, which takes as input a strategy of the maximization player, a strategy of the minimization player, and outputs, let's say, a number that lies in some bounded range, bounded by B. We sort of discussed a little bit last time that you can shift everything by a constant. So if you wanted this to have negative range, it would be fine. The only sort of thing that's going to be relevant is that the difference between the smallest payoff and the biggest payoff can't go to infinity. Okay. Okay. And like Max would like the number that comes out of this to be big, Min would like the number that comes out of this to be small. And the thing that complicates their strategic thinking is that they need to play at the same time. Okay, like, if sort of as we discussed last time, if Min committed up front to what she was going to do, if Min told Max what action she was going to play, it would be easy for Max to figure out how to play. He would just best respond. Once we plug in one of the arguments to this function, Min's action, then if Max wants the output of this function to be big and he's controlling the only remaining argument, he should just choose the action that maximizes the function. Similarly, if Max told Min what he was going to play, right, that would fix Max's input to this function. Min would be in control of a single argument function, taking as input her own action. If she wants the function to be small, she would just play the action that minimizes the function. And we called those things best responses, the sort of minimizer and maximizer of these functions respectively, fixing the argument controlled by the other player. The thing that in general makes it difficult to think about strategic play is that these functions have arguments controlled by players other than you. You don't know what they're going to play, and you don't know how you should, what action you should choose to maximize your payoff or minimize your cost without knowing what the other arguments are. That's in general the thing that makes it difficult to play in strategic interactions. Okay, does that make sense? Okay. So we defined sort of payoff relevant quantities in these games that sort of map onto how well you could do in the game if rather than playing the game simultaneously with your opponent, you played sequentially in one of two orders. Okay, we could imagine the ordering in which Max has to go first and announce his strategy to his opponent, who then gets to best respond. Okay, this would put Max at a disadvantage because he'd have to reveal information to his opponent. Or we could imagine the ordering in which Min has to go first, in which Min is put at a disadvantage. Min has to select and commit to an action and then announce it to Max and allow Max to best respond. Okay? In general, these are sort of two different quantities which we can associate with the game, which we called the maxi-min value or the mini-max value, depending on the ordering of play we were imagining. Okay. Okay. So the mini-max value of a game is, we wrote this as V minimax. And this is the payoff that's obtained when min goes first. That's why min comes first in minimax. When min goes first, commits to an action, announces it to max, and then max has the luxury of best response. Okay, so the minimax value of the game is what we get when first min optimizes over her actions. She minimizes over her action space. The action, right? She's choosing the action in her action space that will result in the lowest payoff after max best responds to it. So what is she minimizing? She's minimizing the maximum over max's actions of the utility that will be obtained when A1 and A2 are played. Okay, so right, it's a min-max value. What's going on? Well, she knows that after she commits to her action A2, Max is going to best respond. He's going to pick the action that maximizes his utility. And so min is going to play so as to minimize the payoff after Max's best response. That's why it's called a min-max value. Okay. And then we can also consider the sort of symmetric quantity, the maxi-min value, that results when Max is put at the disadvantage, when Max has to go first and commit to an action that min will best respond to. So the maxi-min value is the value obtained when Max goes first. So Max first chooses an action in his action space. And what's he maximizing? Well, he's maximizing his utility after min best responds. And how's min going to best respond? Well, she's going to play the action that, given knowledge of Max's action A1, minimizes his utility. Okay, so this is just the sort of play when Max has to go first, knowing what min is going to do. Yeah.
And so the idea is that in a zero-sum game, anything that helps me.
Exactly, and that's why we can talk about only a single utility function. In general, in a game, I would have a utility function, you'd have a utility function, every player would have their own utility function. But in a zero-sum game, which is strictly adversarial, if your utility function is simply the negative of mine, then rather than thinking about you maximizing your own utility function, we can just think about you minimizing mine. It's the same thing. And that's why, yeah, so that's why we can think about Max's and min's objective as described in terms of the same function, but with the desire to either maximize or minimize it. Good. Okay, so does this make sense? We can also talk about minimax and maxi-min strategies in the game. Those are just the strategies A1 and A2 that realize these outer maxes and mins, like the actual strategy that max and min would play respectively if they went first. But right now we're just defining the values. Okay. So the nice thing about like sequential play like this is that there's a clear prescription for how to act rationally, right? Like simultaneous move play is complicated exactly because I need to choose my action without knowledge of what you're going to choose, and your action is payoff relevant to me. That complication is gone in sequential play because, I know that if you're, a purely rational, payoff optimizer, I know what you're going to do as a function of my action. And so I can choose what I should do optimally with that knowledge. Okay, so sort of when there's sequential play, in principle, we can just sort of reason by backwards induction in this way, in a way that in general, we can't in simultaneous move play. That's why sequential play is sort of easier to think about than simultaneous move play. But, like it matters who goes first in general. Like, there's the max-min value. It could be different than the minimax value. Okay. So I've been speaking informally as if it is a disadvantage to go first. I've been saying sort of that the player who goes first is at a disadvantage because they are, the intuition is that they are forced to reveal information about what they're going to do. They have to tell it to their opponent. And yet they're not constraining what their opponent can do. They're not constraining the opponent's action space, and their opponent's goals are purely in conflict with their own. And so it can only be a disadvantage to reveal information to them. Okay, but like, let's just make sure that's true. Let's prove a relatively straightforward lemma formalizing that intuition that says that going first can only be a disadvantage in zero-sum games. That's right. Yeah, in general, like, yeah, in general, if it's not a zero-sum game, there can be value in commitment. Like if it's a coordination game, if we're deciding whether we're going to go to a football game or the opera, and I hate football games, but like hanging out with you, I can sort of say, like I have spent, like $500 on opera tickets already. Like I've got 2 of them, like I'm not going to the football game. If I do that, that pressures you to go to the opera with me, and it can be a first mover advantage. Yeah, so like this intuition wouldn't hold true if the game was not zero-sum. So, because of that, let's just check our intuition and make sure that it really is true in a zero-sum game, that going first cannot be an advantage. And so what does that mean, cannot be an advantage? What should the formal statement be? Well, say Max goes first. Max would like to maximize the utility. If going first is a disadvantage, that should mean that the value obtainable when Max goes first, the maximin value of the game, should be only smaller than the value he can obtain if he gets to go second, the minimax value. Similarly, if min would like to minimize the payoff, so if it's a disadvantage to go first, it should be that the minimax value of the game she can get if she goes first, is only larger than the maximin value. And that's what it would mean to be a disadvantage to go first. Okay. So that is in fact the case. The lemma says that in any zero-sum game, the minimax value can only be larger than the maximin value. Okay, like you're Max and you go first, you're only gonna have smaller payoff than if you get to go second. Going first is a disadvantage. And this is true without any further assumptions on the game, right? So we've sort of foreshadowed that maybe eventually, in order to prove the minimax theorem, which is not just this statement, but the reverse as well, we're going to need to assume some structure, something that would sort of let us run no regret algorithms, something like convexity maybe. But so far, we haven't assumed that. The payoff function could be anything, it just has to be bounded. In fact, I'm not even sure we need sort of boundedness for this direction. The action spaces can be anything. We just need that best responses are well defined, which is why we're assuming these spaces are closed and bounded, but they're not necessarily convex. Okay, so this is like the easy direction, and this is true quite generally. Okay, questions about the statement of the lemma. This is sort of like the easy direction of the minimax theorem that says that and formalizing, you know, like the very natural intuition that going first can only be a disadvantage. Okay, so let's say that A1 and A2 are maximin and minimax strategies, respectively. Okay, so A1 is a maximin strategy for max. A2 is a minimax strategy for min. Okay, so like by definition, you know, the minimax value is the maximum over all of Max's actions of U A2, right? Because a minimax value, you know, like if A2 is a maximin strategy, sorry, if A2 is a minimax strategy, that means it is a strategy that realizes this outer minimization. And so the minimax value comes from solving the inner maximization. Right? So the minimax value is just the solution to this inner maximization problem that maximizes the payoff, given that that min has committed to this minimax strategy. Similarly, the maximin value of the game is just the solution to this innermost minimization problem. The minimization problem over all of min's actions. Of the utility, given that max has committed to a maximin strategy. Okay, right, like, yeah, just saying the way we compute the minimax value and the maximin value, given that one of the players has already committed to a solution to the outer optimization problem, is just to solve the inner optimization problem. Okay. So what do we have? The minimax value of the game, as we've already seen, is just the maximum for all of Max's actions of the utility obtained when Max plays A and min plays A2. And this is only bigger than the utility obtained when Max plays A1 and min plays A2. Right? Because, you know, A1 can't do any better than maximizing this quantity. Okay, so if Max plays A1, you know, this can only be worse. And this can only be bigger than if min optimizes over all A in her action space of the utility obtained when Max plays A1 and min plays A, because again, whatever this is, it can't have utility that is smaller than the minimizer in min's coordinates. But this is just the maximin value. Okay. So very straightforward. It is only a disadvantage to go first. And this is an extremely robust statement. It required sort of very few assumptions. We didn't assume action spaces were convex. We didn't assume any kind of convexity or concavity of the utility function. You know, you never gain an advantage in a zero-sum game by going first. Does that make sense? Okay. Now, in general, if we don't assume any of that nice structure, then it can be a disadvantage to go first, right? Like, suppose we're playing rock, paper, scissors, and I'm not allowed to randomize. The only actions I have are deterministically playing rock, deterministically playing paper, or deterministically playing scissors. If I go first, I'm always going to lose. And if I go second, I'm always going to win. Right? So this is an example of a game where the maxi-min value is not equal to the mini-max value. Right? It's going second wins the game for me, going first loses the game for me. So there's no hope that we can sort of stare at this and like decide, oh, like actually these have to be equalities. The mini-max value is equal to the maxi-min value. Like, no, at the level of generality that we're talking, going first really is a disadvantage. Okay. But under various regularity conditions that we will encounter quite frequently, so this is going to be sort of a powerful theorem, it'll turn out that although going first can never be an advantage, it need not be a disadvantage either. It'll turn out that under sort of somewhat general conditions that are going to be useful for us for a wide variety of problems, in zero-sum games, the minimax value is actually equal to the maxi-min value. Okay, and this is called the minimax theorem, and it's sort of the fundamental theorem about zero-sum games, and zero-sum games turn out to be quite general. So this is equivalent, for example, to linear programming duality, if you've studied optimization, or even the version we're going to prove equivalent to sort of convex programming duality. Okay, but we are going to need like stronger assumptions than we've made, because this rock, paper, scissors example tells us that like the minimax theorem that says the min-max value is equal to the max-min value is just not true at the level of generality we've been working at so far. Okay. Here's the minimax theorem. Fix a zero-sum game such that the strategy sets a min and a max are closed, bounded, and convex. Okay, so convex is a new requirement on top of the way we define zero-sum games generally. And suppose also that the utility function, which remember before we assumed was this arbitrary function from pairs of strategies to a bounded range, now additionally satisfies two more constraints. One, that for every action of mins, if I look at the utility function as a single argument function, if I plug in the action of min into the utility function and now look at the remaining function, which is a single variable function only of Max's actions, that this function is concave and Lipschitz continuous. Okay, so if I fix min's action, then as a function of Max's action, the utility function is concave. And if I wiggle Max's action by just a little bit, remember these are vectors in some vector space, if I wiggle it by just a little bit, the value of the utility function doesn't jump sharply. Remember that was the definition of Lipschitzness that we saw last time. Okay, so this is a condition constraining what the utility function can look like as a function of Max's action. We're going to require the sort of a symmetric condition on what the utility function can look like as a function of Min's action. So the symmetric condition is for each one of Max's actions, if I look at the utility function, plugging in, fixing Max's action and looking at it as a single argument function just in terms of Min's action, that as a function of Min's action, this function is convex and Lipschitz. Okay, so the function has to be Lipschitz in both of its coordinates. It's got to be concave in Max's actions. Max is trying to maximize payoff, and maximizing concave functions is a nice thing to do. And it should be convex in Min's action. Min's trying to minimize payoff, and minimizing convex functions is a nice thing to do. Yeah. Let's see what counts as intuition. Like, yeah, good. So let me maybe finish writing down the theorem, talk about standard bimatrix games, and then maybe I'll try to pass off the Lagrangian of a convex program as intuition. Okay. But first of all, these are the conditions. Okay, like convex in one place. First of all, so what's new? The action spaces are not now merely closed and bounded, but they're convex. So the action spaces, I can take any two actions in the action space and interpolate between them, and anything I get by interpolating between those two actions is still an action in the action space. Okay, this is something that is not satisfied by my no randomization allowed version of rock, paper, scissors, where we saw the minimax theorem does not hold. Similarly, my utility function has to be concave in one player's action, convex in the other. It's okay, for example, if it's linear in both. And if that is the case, then the claim is that the minimax value is actually equal to the maximin value. Okay, so although it is never an advantage to go first, if these conditions are satisfied, it's also not a disadvantage. Okay, so let's sort of maybe, first of all, talk about standard matrix games like rock, paper, scissors, of the sort you're most familiar with, and maybe have encountered the minimax theorem in that setting before. So if you take a game like rock, paper, scissors, or more generally what are called bimatrix games, where like basically I have some finite number of actions, you have some finite number of actions. There's just some matrix out there that's telling us for every one of my actions paired with one of your actions, what is my payoff? Okay, so for games like that, and this is sort of the setting in which the minimax theorem was originally proven. This is the setting of von Neumann's minimax theorem. In games like that, when you sort of start off, it would seem like you don't satisfy the conditions of this theorem because your strategy space is like some discrete thing. It's definitely not a convex set. I've got like discrete actions like rock or paper or scissors. And indeed, it's not just that it seems like it doesn't satisfy the conditions. It doesn't. Like rock, paper, scissors was the example we gave to see that the minimax theorem does not in general hold. So what do you typically do to cause the minimax theorem to hold? Well, you say, okay, I'm going to expand everyone's strategy space to allow them to randomize. So I said previously, you had some finite number of actions like rock or paper or scissors. I'm going to take the convex hull of that set of actions, the set of all probability distributions over that set of actions, and call that your new action space. Okay, so now if I'm allowed to randomize, if this is rock and this is scissors, there's stuff in between. I can interpolate between them. These are the distributions, the probability distributions that range from putting 100% of my weight on rock to 100% of my weight on scissors, but there's stuff in between, like I can randomize 50-50 between rock and scissors. Okay, so the reason why mixed strategies are useful in game theory, one reason why, is because mixed strategies correspond to the convex hull of some set of actions. And so by allowing people to randomize, I'm making their strategy space convex. Okay, satisfying the first requirement of the minimax theorem. Okay, how about the second ones? Well, like in rock, paper, scissors, or in any matrix game, what you've specified up front is the utility that I get for any pair of actions that are played. For example, if I play rock and you play scissors, I win. I get payoff 1. Whereas if I play rock and you play paper, I lose. I get payoff 0. Okay? Well, how about in between? Like, we've just expanded the strategy space to allow these mixed strategies. We've taken the convex hull. How do we define our payoff in between? Well, the way that is typically done is we sort of say, okay, if I'm randomizing, I'm playing some mixed strategy, some distribution over my actions, and you're randomizing, you're playing some mixed strategy, some distribution over your actions, then I'll define my payoff as my expected payoff when I sample an action, a pure strategy, from my distribution, and you sample an action, a pure strategy, from your distribution. Okay, but this means that my utility for strategies that involve randomization is defined as an expectation. Now, expectations are linear. Okay, so that means that when I define utility functions in this way as my expected utility when I sample an action from a distribution, actually by linearity of expectation, the utility function is linear in the actions of both players. And so in particular is convex and concave as required. Okay. Now, we can define things more generally than that. So, I said that the minimax theorem was equivalent to duality in convex programs, right? What does that mean? I'm going to say some stuff here that if it doesn't make sense, don't worry about it. But in general, in a convex program, you have some convex objective you'd like to minimize, subject to some convex constraints. Okay, and there's various, good reasons for convexity in various settings. Sort of corresponds to like increasing marginal costs. Now, I can express a constrained optimization problem, like minimize some objective subject to some constraints, as an unconstrained problem through its Lagrangian. I want to minimize the objective plus some weighted combination of the constraints, where, if you like, an adversary is controlling the weight on the constraints. Okay, so you can think about this as sort of saying, like, forget the objective for now. Let's say I want to satisfy, I want to find an assignment of variables that satisfies a collection of constraints. Okay, well, we could frame this as a zero-sum game where I pick the assignment of variables and the adversary picks the constraint. And the cost I suffer, which I want to minimize, is the violation of the constraint chosen by the adversary. If I pick something feasible that satisfies all of the constraints, then my payoff is 0. My cost is 0. That's what I wanted. But if I pick something infeasible, the adversary can pick the most violated constraint, which will, if it's violated, will give me positive cost. Okay, So, you know, if I get to go first, I could pick a feasible solution. And so the value of this game, you know, the mini-max value of this game would be 0. And so, yeah, so like finding a solution can be framed as finding a minimax solution to this game. And, you know, like whenever the constraints are convex, I can do this because it'll satisfy the conditions of this theorem. So whenever you have a convex program, that's like an example of when you might want to apply like a version of this theorem that extends beyond like linear utility. Then you never heard of convex programming or linear programming, just like ignore that last part. Okay. Okay, so questions. So the minimax theorem, the thing we want to prove, is sort of like the opposite direction of this theorem. It requires some more conditions. The thing that was straightforward was that it is no advantage to go first. But if the additional conditions are satisfied, it says it's also no disadvantage going first. Okay, and like when we're thinking about rock, paper, scissors like games, randomization is important because it's what satisfies the conditions, and it's what makes the difference between me needing to commit to a strategy like I'm definitely going to play rock, which is a bad idea for me to tell you, to committing to a strategy more like I'm going to play rock a third of the time, paper a third of the time, and scissors a third of the time, which is the thing I can tell you without causing a disadvantage. Okay. Okay. Now, one thing I want you to notice is that the conditions I've imposed here are sort of similar to the kinds of conditions we've been talking about when we've been studying online convex optimization algorithms. Okay, so, you know, like our action spaces, when we talked about online linear and online convex optimization, they had to be convex. I'm now requiring that of the action spaces here as well. When we talked about cost minimization, we were able to do that when loss functions were convex and Lipschitz, right? Like, you remember this reduction from last class where we sort of reduce online convex minimization to online linear minimization by treating as our cost function the gradient of the loss. And the Lipschitz parameter controlled the magnitude of that gradient. So it was important not just that the loss be convex, but Lipschitz. For the minimization player, the player who's trying to minimize this thing, we've required that the losses they face, no matter what the maximization player does, be convex and Lipschitz. Okay, and you know, just as we can do online convex minimization just by multiplying everything by -1, we can do online concave maximization. And similarly, we've required that the gains faced by the maximization player, no matter what the minimization player commits to, are concave and Lipschitz. Once again, exactly what we need in order to be able to run no regret algorithms like online gradient descent or follow the perturbed leader or multiplicative weights. Okay. Okay, so this is no accident. We are going to prove the minimax theorem by making use in the proof of these algorithms we've derived, right? Which is sort of interesting, by the way. Like, this is not an algorithmic statement. This is just a structural statement about zero-sum games. So it's not like we need to like give an algorithm. The algorithm is purely going to be, you know, a tool of our analysis. We are going to prove this theorem by engaging in a thought experiment that will involve algorithms like online gradient descent. Okay. Okay. Okay, so what is this thought experiment? Okay, so first of all, what do we need to show? We already know the easy direction. We already know that the minimax can only be bigger than V maxi min. We know it's a disadvantage to go first. The thing that we need to argue cannot happen, subject to these conditions, is we need to argue that this inequality cannot be strict. We need to argue these things are exactly equal. Okay, so if the, suppose for point of contradiction that they weren't. Okay, suppose that actually epsilon, the name I'm going to give to, let's say, the difference between the minimax value and the maximin value, let's suppose this was actually strictly bigger than 0, right? That it was actually like actively a disadvantage to go first. You would lose epsilon in utility. Okay, like this is what we want to show can't happen. We want to derive a contradiction starting from this premise. Okay, so I said we were going to do this by engaging in a thought experiment. Let's lay out what that thought experiment is. So let's imagine repeated play of the game for T rounds. Okay, which results in a sequence of action pairs, one for each player. So every round, let's say that Max plays AT and Min plays BT. Okay, so we have a pair of actions played by each of the players at each round, little t, and this ranges from 1 to big T. I haven't told you how they're choosing their actions yet, but I want you to get in the mood of sort of imagining that Max and Min are repeatedly playing this game with one another. Okay, meaning at each of T rounds, they each select an action, AT and BT. Okay, this goes on for capital T rounds. Okay. So now I need to specify how exactly they're going to choose these actions. All right, so since we know that for each of these actions that Max chooses, the utility function that we get when we plug in Max's actions as a function of Min's actions is Lipschitz and convex. We'll let Min choose her actions BT using an online convex optimization algorithm. Which will feed loss functions LT, defined just as the utility obtainable given the selection of Min's actions. Okay, so just to like be clear about what we're saying and that we're allowed to do this, right? Like what do I need to set up? I'm saying that Min and Max are repeatedly playing in an interaction against one another. So far, I haven't specified how. Okay, I haven't said yet how Max is going to choose his action.
regret bound is the concern for the it feels like, no, maxing in, the min might choose a different action, and that would get you a better outcome than it's supposed to be the same.
Yeah, well, remember the minimax and maxi-min value of the game, they're not about repeated play, right? It's just about a single sequential interaction. I pick first and then you go second. Yeah. Okay. Okay, so let's sort of go through this. So what we're going to do is we're going to analyze the cumulative payoff of this game over T rounds from two perspectives, from the perspective of max and the perspective of min. And we're going to, these two analyses are going to sort of together prove the theorem. Okay, so let's first look at the long run payoff from the perspective of min, who enjoys this nice no regret guarantee since she's playing an online convex optimization algorithm. So what do we know about algorithms like online gradient descent? Well, if we look at the cumulative payoff over all of the rounds, okay, so the sum over all of the rounds of the utility obtained when max plays AT and min plays BT, or equivalently, the sum of the losses of online gradient descent for the sequence of actions BT played by online gradient descent, since this is how we define the losses. We know that the cumulative losses of online gradient descent are no more than the loss of the best fixed action in hindsight plus a regret term. So the regret bound of online gradient descent or similar algorithms says that this cumulative loss is no more than the minimum over all of the fixed actions of min of the cumulative loss min would have obtained had every day she played this fixed action B and max played the same sequence. That's what these counterfactuals for regret say. It's the same sequence of loss functions, but min played some fixed action B, and the cumulative loss that min experiences is no more than the cumulative loss of the best fixed action in hindsight. Okay, not exactly that. There's a regret term that is always, for all of the algorithms we've seen, on the order of 1 over root T. I'm putting this in big O notation because the actual constants here will depend on things like, for example, the Lipschitz constants, which we haven't specified. Okay, so there's some constants here that depend on parts of the game we haven't specified, like potentially the dimension of the action space of min and max, the scale of the payoffs, this number B, the Lipschitz parameter of the utility function. But we've assumed all of those things are bounded, so those are all constants that depend only on the game and are independent of T. And for all of the algorithms we've seen, there are regret bounds that go to 0 at the rate of 1 over root T. Okay, makes sense. This is just sort of reiterating what a regret bound is. Sort of says you perform as well as the best action in hindsight. Okay. Now, what are we doing over here? We've got a fixed action for min, and we're averaging over the utility. We're averaging over the utility obtained for many different actions of max. Okay, now, max's utility function, the utility function, if we fix min's strategy to be something B, right, it's concave in max's actions. So it's something that looks like this. Okay, so when we average the utility of 2 points, that's like, linearly interpolating between the 2 points on this concave curve, that's only smaller than if we evaluate the function at the average of those points. Okay, that's called Jensen's inequality. Okay, it's a property of concavity that we're going to use. And so we know that this is, at most, the minimum over all of Min's actions of the utility of the average of Max's actions when Min plays B. Okay, here we've used two things. Because the utility function is concave in Max's actions, rather than taking the average of the utilities, we can take the utility of the average, and that only makes this quantity larger. That's Jensen's inequality. And also because Max's action space is convex, since all of these actions AT were feasible actions, the average of those actions is also feasible. Okay, so in this step, we're using two things. We're using the fact that the utility function is concave in Max's actions, and we're using that the action space is convex. Okay. Okay. But this is some fixed action, the average of A1 through AT. That's some fixed action for Max. This is the utility that Min gets when she best responds to that action. When she knows Max's action up front, and then chooses her action to minimize the utility. Okay? So this cannot be more than the maxi-min value of the game. The maxi-min value of the game is the value obtainable when Max optimally commits to some strategy and then Min best responds. Here, Max has committed to some strategy, not necessarily optimally, and Min has best responded. Min wants to lower the cost, and so this is only smaller than that. Okay, so this is at most the maxi-min value of the game plus 1 over root t. Okay, so this is the analysis from Min's perspective, and I just want to make sure it makes sense. Okay, like just 3 lines, but let's just make sure we understand them all. The first is just the regret guarantee of online gradient descent. Okay, when we're minimizing convex losses, Lipschitz convex losses, online gradient descent says our cumulative loss is at most the loss of our best action in hindsight. Our cumulative loss to the best action in hindsight is for a fixed action of Min, an average over these utilities, over a bunch of actions of Max, which is only smaller than the utility of Max for the average of those actions. That's from concavity, and this is a legal thing to plug into a utility function because of the convexity of Max's action space. And this is a regime where Min is best responding to a particular action of Max, and so, is upper bounded by the maxi-min value, which is exactly what Min can get if she best responds to an action of Max that Max chose optimally. Okay, and so from the no regret guarantee of algorithms like online gradient descent, we have established that the average utility obtained over these t rounds is at most the maxi-min value of the game plus a regret term that we know how to drive to 0 at a rate of 1 over root t. Is that clear? Okay. On the other hand, like term by term, like forget the average, like we also just know that term by term, at every round, if I look at the payoff at that round, it is at least the minimax value. Right? Because what was our thought experiment? In our thought experiment, Min goes first and commits to her action using online gradient descent, and Max best responds. Right? So in the thought experiment, Max goes second. Well, the minimax value is the value that Max can guarantee if he goes second, even if Min plays optimally. Here, she's not necessarily playing optimally every round, she's just playing something. Max is best responding, so he only gets higher utility. So his utility at each round is at least the minimax value, and therefore his average utility over all of the rounds is also at least the minimax value. His average utility, his pointwise utility is at least the minimax value. Okay, so combining, we know that the minimax value is at most the average utility obtained over the t rounds of this thought experiment, which is in turn at most the maximum value plus something that goes to 0 at a rate of 1 over root t. Okay, so this regret term, it's going to 0 with t. But t lives only in our minds. T is part of our thought experiment. So we can take t to be as large as we want. In particular, if we want this term to be less than epsilon, we can arrange that by just taking t to be large enough. So by taking t to be large enough, we get that, well, the minimax value minus the maximum value is less than epsilon. But epsilon was supposed to be exactly equal to the minimax value minus the maximum value. So this is a contradiction. And so our premise that the difference between the minimax and the maximum value was some quantity other than 0 has just been falsified. Right? The only value this could take, which wouldn't lead to a contradiction, is 0. And so the minimax value is equal to the maximum value. Right? So that's the minimax theorem. It says that under these sort of very general conditions, going first is in fact no disadvantage at all. And the conditions are not arbitrary conditions. They're the conditions needed in order for this thought experiment to work. What did we use? We used that the conditions were satisfied to allow Min to run a no-regret learning algorithm like online gradient descent. We also used that Max's utility was concave and that his action space was convex, which, as it happens, are also the conditions we would have needed for him to run a no-regret learning algorithm, which is no coincidence because the situation is symmetric. Rather than having Min run a no-regret learning algorithm and Max best respond, we could have done the thought experiment in the other way around. Okay, so at least with this proof technique, it's sort of very clear in one direction, the link between no-regret learning algorithms and the minimax there. If tomorrow you told me about a new no-regret learning algorithm that worked under less restrictive conditions, then I would immediately have a new minimax theorem that worked under less restrictive conditions by just swapping out what algorithm is being run. And the reverse is true as well. So what we're going to do a few lectures into the future is start with a minimax theorem, and from that derive from first principles a no-regret learning algorithm. So this is sort of going to be a sense in which there's a very tight connection between no-regret learning and minimax theorems.
So I just wanna, I mean, the bottom right column. is- So the first, the one on the left is
The minimax is less than the maximin plus
plus
a term going to 0.
But that's.
That's right. So subtracting from both sides, the maximin value, the difference between the minimax and the maximin value can be driven to 0.
Okay. And then so since it's so less than, but also.
That's right. So like the easy direction, the thing we proved first in this class was that epsilon was greater than or equal to 0. It's only a disadvantage to go first. We just showed it can't be greater than 0 because for any positive number, we can sort of falsify it by running this thought experiment for long enough.
Okay.
And so it must be exactly equal to 0. Make sense?
Yep.
Okay. Good. All right. So now we know the minimax theorem. So we can sort of stop talking about maximin and minimax values of the game as distinct things, at least in zero-sum games for which we know the minimax theorem to hold. We can just talk about the value of the game. Okay, so in any zero-sum game, such that the minimax theorem holds, let's say that the value V of the game is the unique value V such that the minimax value of the game, which by the minimax theorem equals the maximin value of the game, is V. So if the minimax theorem holds, we don't have to talk about the maximin or the minimax value of the game anymore. We know those are the same thing. We can just talk about the value of the game. Natalie. Mostly. So if you look up sort of the fanciest minimax theorems, they might go slightly beyond in various technical ways. The settings for which I know statements that exactly map onto no regret learning algorithms, but morally they're the same thing. So yeah, if you're interested in sort of exact tightness of all of these conditions, that might be a good like topic for a course project. I don't know. You know, if you look up like Sion's minimax theorem, which is sort of defined in terms of very general sort of measure theoretic conditions, all of the important ones are the same. You need concavity, convexity, you know, convexity of the action space, but things are defined in maybe a little bit more generality than what I was able to prove right here. And whether you can exactly get no regret algorithms exactly when you can get the most general min-max theorems, I'm not sure of the details. Yeah, it's a good question. I don't know what's known about that exactly. It may just not be understood. So it might be a good course topic project. Course project topic. Yeah. Oh, well, it doesn't show up in the theorem, right? Like the theorem's not about a repeated game. The theorem's about a zero-sum game, and it's about, you know, the advantage of going first versus, and we'll connect it also to simultaneous play in a moment. Right, so like the whole aspect of repeatedly playing this game for T rounds, that showed up only in the proof. That's not in the statement of the theorem. Right? I mean, like the statement of like this whole interaction for T rounds that just doesn't appear in the statement of the theorem, right? That was part of how we proved the theorem, but it's not like I didn't need to talk about repeated anything to state the minimax theorem. Okay. Okay. Okay, so the minimax theorem has many interesting consequences, algorithmic and otherwise, but let me finish off the class today by just sort of stating one immediate consequence in terms of strategic thinking in zero-sum games. So remember, we sort of said, okay, well, in sequential play, it's sort of easy to reason about how you should play. You just sort of engage in this backwards reasoning. For each of my actions, what would my opponent do if they knew I was going to do this? Okay, so then I should do the thing. I should commit to the thing that would cause them to choose the action that would maximize my payout. Okay, so you can sort of engage in this sort of straightforward sequential reasoning if you have to go first and commit to what to do. Similarly, if you have to go second, it's even easier. You just look at what your opponent is doing and you best respond. The tricky thing, it seems, in strategic interactions is if we have to play at the same time, because I have to commit to an action without knowing what you're going to do. Okay? In zero-sum games, the minimax theorem implies that it is just as easy to reason about sequential play as it is to reason about, it's just as easy to reason about simultaneous play as it is to reason about sequential play. Like, because it doesn't matter who goes first, like basically I should do the thing I would have done had I gone first, even if we're going to play at the same time. So remember, like, what was our solution concept for simultaneous move play? It was Nash equilibrium. A stable state, Nash equilibrium is a stable state of the game where somehow both of us are simultaneously best responding to each other's actions. And in general, it could be hard to find a Nash equilibrium at some fixed point problem. But in a zero-sum game, in which the minimax theorem holds, a pair of strategies A1, A2, one for the maximization player and the other for the minimization player, is a Nash equilibrium if and only if A is a maxi-min strategy and A1 is a maxi-min strategy and A2 is a minimax strategy. Okay, so sort of Nash equilibria in zero-sum games correspond exactly to optimal sequential play in zero-sum games. The only way you can have a Nash equilibrium is if max is playing a maxi-min strategy and min is playing a minimax strategy. Okay, so what this is saying is that in general, although it might be more difficult to reason about how to play in simultaneous move games compared to sequential games, that's not the case for zero-sum games. For zero-sum games, you can reason sequentially and play simultaneously. Yeah. So let's see. So there are interesting questions there that you can talk to Natalie about. Strictly speaking, that doesn't type check. Like playing, like in a game, like you play one of your actions in a max if you're max, and those are not algorithms, those are vectors, right? So in a game, you don't play a no regret algorithm, you play an action. Now you can talk about of course, playing algorithms in repeated play of the game, like in our thought experiment. Now, if you define that as a larger meta game in which your strategy space is the set of algorithms you could play, then yeah, now it's some much bigger game, and you can ask, is it an equilibrium if I play a no regret algorithm and you play a no regret algorithm? Actually, in a zero-sum game, that should be sort of true up to these low order regret terms. In general, it's not true. But yeah, like in zero-sum games, I guess up to these like 1 over root t things, then yes. Yes, the proof would also work if both players were using no regret learning algorithms. That's right. And if I'm using a no regret learning algorithm, then there's no way you can exploit me beyond the regret bound in a zero-sum game. Good. And there's a bunch of papers that, sort of about thinking about best responses and equilibria in algorithm space, and whether when and whether it is a good idea to play no regret algorithms if your opponents know that you're playing no regret algorithms and are going to choose their algorithms in response. And so there's interesting stuff to think about there. Okay. Okay, so let's let V be the value of the game. Okay, the minimax theorem is satisfied, so we're justified in speaking about the value of the game. So if A1 and A2 are maxi-min and minimax strategies respectively, we know that the utility obtained when we play A1 and A2, on the one hand, is at most V, and on the other hand, is at least V by invoking the minimax and maxi-min claims respectively. And so it's exactly equal to V. So if we're both playing minimax strategies, the payoff we're obtaining is exactly V. Okay. Okay, but since min is playing a minimax strategy, which forces the payoff below V, and yet we as max are obtaining payoff at least V, that means that A1 must be a best response to A2, because A2 is forcing payoff to be at most V, and yet we're obtaining payoff at least V. So we're best responding to min. Similarly, A2 must be a best response to A1, since A1 is a maxi-min strategy, which forces payoff to be at least V, and yet we're, as min, obtaining payoff at most V. We're best responding to it. So A1 and A2 are both best responses to one another. So if they're both minimax and maxi-min strategies, respectively, they are also a Nash equilibrium. How about in the other direction? Well, suppose that A1, A2 is a Nash equilibrium pair. Okay, well, in particular, A1 and A2 are best responses to one another. A1 is a best response to A2. Now, one thing that player one could have done, that Max could have done, is he could have played a maxi-min strategy, okay, which would have forced the payoff to be at least V, no matter what min did. Since A1 is playing a best response to min in a strategy space that includes a maxi-min strategy, that means that the utility has to be at least V. Otherwise, it couldn't have been a best response because he could have forced payoff V by playing a maxi-min strategy. Similarly, since A2 is a best response to A1, and min could have played a minimax strategy, it's also got to be that the utility is at most V. Okay. So the utility is exactly V. And since we've established that, so the utility is exactly V. And since both players are best responding to one another, okay, it must be that they're both playing minimax and maxi-min strategies respectively. Since if one of them wasn't, then the other player best responding to it would have obtained utility either strictly above V or strictly below V. Okay, so the reverse direction is true as well. So one consequence of the minimax theorem in terms of strategic thinking in zero-sum games is that the nature of strategic thinking in sequential games is the same as the nature of strategic thinking in simultaneous move games, at least when the minimax theorem is satisfied, because Nash equilibria, when the minimax theorem is satisfied, are in one-to-one correspondence with pairs of min-max and max-min equilibria. Okay, I'll see you guys next time on Wednesday. What I'm going to do, and I'll post this on the Slack, I'm going to, so next class, rather than lecturing, I'm going to use the time to talk to folks about their project ideas. So I'm going to, on the Slack, put a little sort of sign-up sheet for 10-minute intervals, do some brainstorming with your group mates about what you might want to do or talk about. You're not obligated to talk to me on Wednesday about this, but it's an opportunity to.